Hello, my name is Carlos Huerta. I'm a technical marketing manager here at Micrel. And today I'm joined by Rana Yetka, our senior application engineer. Today, we're introducing the 23450 and 51, a new product, triple buck, that is very easy to use, offers high efficiency, only requires 23 microamperes of quest current per channel. Very simple solution. So let's talk a little bit about those key features. The MIC23450 and 51 have an input range between 2.7 volts and 5.5, making it ideal for battery type applications. It also has low quiescent current, only consuming 22 microamperes to 23 microamperes per channel. Again, as I mentioned, three different outputs, independent outputs, 2 amps per channel capability. It can be adjusted down to 1.4 volts. It does incorporate our HyperLight load technology, which, as we will discuss later, offers very low output ripple and high efficiency throughout a wide range of loads. It offers independent enables for power sequencing and also has 3 independent power goods signals. Again, it offers HyperLight load technology enabling up to 93% of efficiency. So an example, with a 3 volts in, 2.5 volts out at about 400 milliamperes, you can achieve up to 93% efficiency. The 23450 and 51 are offered in 2 unique packages, a 4x4 and a 5x5 leaded QFN package. And as you see, the whole BOM solution only requires 12 millimeters square. So it's an ideal solution for applications that require a very compact design. So now, Rana, let's talk a little bit about some of these key features. I'd like to understand a little bit more about, and maybe we can also explain to the audience, is how HyperLight load works, and perhaps discuss some of the key attributes of this new topology that we've integrated into our triple buck regulators.
Sure. One of the key attributes of HyperLight load is low IQ, low quiescent current. I can show you as one single output, having one single output on through the wide range of input 2.5 to 5.5, we're measuring 22 microamps, as well as having all 3 of them on, we're measuring 66 microamps throughout 2.5 to 5.5 wide range of input voltages. And that's one of the key benefits of HyperLight load. And the reason, as you can see in the block diagram, the oscillator has been eliminated. That saves us a lot of quiescent current, as well as the control circuit goes into a low power state. So that's why it conserves a lot of quiescent current.
So Rana, what's another key attribute for HyperLight load in terms of a key feature that this technology brings? I think efficiency is one of the things that we were talking about earlier. So can you tell me a little bit more about HyperLight load and efficiency?
Oh yes, sure. One of the main features of HyperLight load is maintaining a high efficiency throughout the whole wide range of loads. As you mentioned, in portable power, efficiency, especially at light load, has a great impact on a battery life.
Yeah, very key for our customers to be able to really extend that battery life, and efficiency definitely is a key importance.
Correct. And in the normal PWM operation, you can optimize efficiency at mid to full load ranges. However, that comes at the sacrifice of losing efficiency at light loads. But to maintain the efficiency high throughout the wide range of output loads, we're using the HyperLight load. So let me show you the efficiency.
Sure.
As you can see, the efficiency throughout the wide range of output loads maintains, depending on the input voltage, maintains up to 93%.
That's excellent.
That's excellent.
So Rana, what are some of the advantages of HyperLight load versus PWM control?
In a PWM control, buck regulator contains of two kinds of losses, DC losses and AC losses. DC losses are mainly determined by the RDS-on of the both MOSFETs, as well as the DCR of the inductor. And AC losses are switching losses, gate drive losses, and dead time losses, which they are proportional to switching frequency.
Okay.
There are different ways to approach the operating efficiency at different loads. So at heavy loads, the DC losses dominates, which means by reducing the RDS on and reducing the DCR of the inductor, we can actually improve the efficiency.
Oh, okay. So that's,
Yes.
that's basically how we get to have peak efficiency of 93% at half an
High
amp, for
loads.
example.
Correct.
Okay.
And at light loads, the conduction losses are insignificant, but the AC losses are dominating.
Okay.
So
That makes sense.
by having the hyperlight load, which has a very, very, very significantly low IQ and switching the switching frequency, then we can improve our efficiency.
I see. So Rana, let's look a little bit into our foils. I want to just get a little insight more into continuous conduction mode, and if you can, maybe perhaps explain
Sure.
how that actually functions.
Sure. As we know, hyperlight load, a continuous conduction mode, contains of two stages, on state and off state. Hyperlight load estimates the constant on time by sensing V out and V in, as well as the off time is controlled by the V feedback. As we know, the T on is equal to duty cycle times the period, and period is 1 over frequency, which is the switching frequency in CCM.
Correct.
And the duty cycle in buck regulator is V out over V in. Let's look at the simplified block diagram. The constant on time is equal to duty cycle times the period. Period is 1 over switching frequency, and the duty cycle in buck regulator, as we know, is V out over V in. And the off time is controlled, and it depends on the V feedback. So by looking at the block diagram, if the V feedback is less than V ref, PMOS turns on, charging our inductor, and NMOS turns off. And as soon as V feedback is greater than V ref, then the PMOS turns off, it's off state initiates, and NMOS turns on, discharging our inductor. The comparator controls the off time while the on time is constant, and frequency stays constant. Now let's look at the hyperlight load in discontinuous conduction mode. As we know, it contains of 3 states: on state, off state, and idle state. The hyperlight load estimates the constant on time from sensing the V in and V out, and the off time is variable based on the feedback voltage. Let's go over the next slide. Hyperlight load consists of constant on time. The T on is equal to duty cycle times the period plus the T recovery. And the T recovery is the time it takes to rebias the turn-off circuitry, which is roughly 100 nanoseconds. And duty cycle is V out over V in a buck regulator, and the period is 1 over switching frequency in CCM. Controlled off time. Once T on is finished, it will initiate the turn T off, and stays off till V feedback is less than V ref. In this time, when the feedback is greater than V ref, the PMOS is off, is discharging our inductor as shown, and when the inductor current reaches 0, the idle state kicks in, which means both transistors are open, and it starts discharging our output ripple. As you can see, the output ripple depends on the load. If the load is lower, it takes longer for the discharge rate of the output ripple to come down. And then while in the idle state, when the feedback is less than V ref, then PMOS turns on, charging the inductor, then the circuitry repeated. And most circuitry is turned off except the current sense and the comparator in the idle state.
Rana, thank you very much for enlightening us as to how the 23450 and 51 achieve such high efficiency through a hyperlight load technology. But I see that you brought a demo, and I'm just curious exactly what else you want to show us today.
Let me show you the transient response.
Okay.
As you can see, I zoomed in, and I'm transiting the current, which is channel 4, from 200 milliamp up to 500 milliamp, and I have channel 2 V out in AC. And if you look, I have a peak-to-peak transient response of 75 millivolts. And I zoomed in enough, it's 4 microseconds per box, so you can see how fast is the transient response. And I have, the conditions are, I have 3.6 input, 1.5 output, and it looks very good.
Yeah, it looks great. Now, if I assume this is kind of performance we get across all 3 channels, so crosstalk regulation, very good as well.
Correct.
Great, great. So if we had customers, for example, I have a couple of customers in the test and measurement arena that they would like to see perhaps a little better transient response. So what would you suggest in terms of trying to make this even a little better? What would you suggest we go about doing that?
You mean to reduce the peak-to-peak transient response?
Correct.
Correct? Yes, we can do that by adding our newest revision of Ripple blocker.
Okay.
Ripple blocker family, which is 94325. Actually, I have a board set up. Would you like me to show you?
Absolutely, yeah, that'd be great to show.
So here it is, Carlos. I attached the 94325, the Ripple blocker, and the output of 23450. I'm feeding it in 2 volts, and the output of the Ripple blocker is 1.5 volts. And as you can see, the transient response, the peak-to-peak voltage measures to be 22 millivolts, which is roughly 1/4 of what we measured without the Ripple blocker.
Great. Thank you, Rana. Thank you very much. So, Rana, we've learned a lot today about the 23450. Certainly I did. Thank you very much for enlightening us a little bit about how HyperLight load works. One thing that stands out to me is the fact that low quiescent current, ideal for battery-powered applications. A lot of customers are going to love that about it. But also efficiency.
Yes, and maintains a high efficiency throughout the wide range of loads.
Great. Very easy to use, guys. Requires very low external components, internally compensated.
As well as the fastest transient response in the industry.
Yeah, so great. For more information, please visit us at Micrel.com. And again, thank you, Rana, for joining us today.
Thank you, Carlos.
And thank you guys out there for watching.